Okay, so this is Math313 number theory. This is lecture 28. I wanted to just do some plots from the last class. So it turns out that there was nothing wrong with the code. The code was absolutely fine at the end of class. What was wrong was that one of the functions that was used had not been recompiled when I opened up the program on the computer here. And Mathematica, in its finite wisdom, rather than saying, hey, I don't know what this function means, actually still computed things and turned out plots. This is not, well, this is being recorded. This is a nice feature of Mathematica. Okay, I would prefer something to say, warning, function undefined. Would you like to define it, please? So there was nothing wrong with the code. So this is a plot of how many steps it takes to come down, on average, starting at different values. Now the first thing you notice, I'm doing a log-log plot. I'm plotting the log of the number of steps versus the log of my starting values. And I'm going over a fairly significant range. I'm starting at 10 to the 10, and I'm going up to like 10 to the 40, 10 to the 50. Okay? So why do you think I'm doing a log-log plot? Why aren't I just plotting how many steps it takes as a function of where I start? You always want to think about how you present your data. How you present data influences how people view it, right? I have chosen to present it as a log-log plot. Well, down here I'm plotting the log of my starting seed. Why wouldn't I just plot the starting seed? Yes? Yeah, the values get more and more spaced out. So if I'm going through your 40 or 50 orders of magnitude, if I were to do a plot on the x-axis, the x-axis would essentially be just the last data point. That's essentially all I would see. Or maybe the last 2 or 3 data points. If you're going through 40 or 50 orders of magnitude and your axis is this big, you really can't see things. Right? And so as long as I'm doing the log of my starting value, I might as well do the log of the output. Does this curve look interesting to you at all? Does this look like a curve you know? Yeah.
It even looks like square root or log.
Yeah, maybe square root or log. It's growing but not exceptionally fast. Maybe we could try to fit it. But maybe I'm actually looking at the wrong thing. I love logarithms. I can justify taking the log of the x-axis, because I'm going over so many orders of magnitude, that's worth doing. Is there a justification for taking the log of the output of the number of steps? No. A lot of times when you do a log-log plot, if you have nonlinear relationships, a log-log plot will show you nonlinear relationships. If I have, y equals x to the r, if I take the log of both sides, I'll get, r log y, log y equals r log x. So in a situation like this, I will be able to see a linear relationship. If I have other things, I can see linear relationships with a log-log plot. But for this, maybe I shouldn't do a log-log plot. All right, so we all agree that it's not immediately clear what shape this is. Let's see what it looks like if we don't do a log-log plot. And just so I'm analyzing 1,000 data points, because I just had this running doing Math331 today, starting at 10 to the 10, going up to 10 to the 40, and using the function that pulls out all the powers of 2 at once. So the 1,000 is not great, but it's not horrible. All right. So if I don't do a log-log plot, this is the shape I get. Any thoughts as to what shape this is? Looks a lot like a straight line. So let's see if I can take 2 pieces of paper. I don't see any long rulers in this class. Math departments have changed since I was a kid. But if I take 2 pieces of paper, that does look pretty straight over several orders of magnitude. So is this a proof that it's a linear relationship? No, we don't even know that the 3x plus 1 problem eventually goes down to 1. But this is strongly suggesting that the number of steps needed is going to be linear in the log of the power. Okay? Not a proof, but it's suggestive. We also saw things that look like Gaussian fluctuations. We have conjectures as to why it should be Gaussian fluctuations, but not proofs. So there's a lot of open problems in number theory that you have enough tools to start studying. We have some progress. I think we know things like, if you look at all the numbers up to x, I think like x to the 0.8 of them iterate down to 1. Well, unfortunately, what percent of numbers up to x is x to the 0.8? So what fraction of numbers up to x would a set of size x to the 0.8 be? 0%. It's even less than the primes. It's better than the perfect squares. That'd be about x to the 0.5. But we have very little knowledge, sadly, as to what's going on. But we can make conjectures and we can model things. And so your problem number 7 that you're going to work on for homework / midterm this week is some stuff related to 3x plus 1. It's going to require you to do some coding. It's going to require you to do some theoretical calculations and to try to make some conjectures. And that's one of the skills I really want you to get out of this class. How would you make conjectures? How would you try to get a sense of what's going on? Okay. Can you hit the mute button? Well, actually, better get power off, power off. We don't really need the... Okay. Excellent. Okay. So I want to now switch gears and go to elliptic curves. So elliptic curves is a beautiful, beautiful topic. And one of the reasons we want to cover elliptic curves is they have applications. And a lot of things in number theory at first, you don't know, does anybody care about this? Is there going to be any use for this? Turns out there's use. What area frequently finds use for things? Yes. Encryption, cryptography. Oh, the lights are on. All right, it's just dim here today. So it turns out we can generalize what we did for RSA encryption and use elliptic curves to do something called elliptic curve cryptography. So if you want an application, this is a great application. And the question is always, which method of encryption is best? Well, what's your definition of best? When I had 2 young kids, people asked me which kid did I love most. And I had a very clear factor. Whoever is sleeping best through the night. That's the kid I love most. Who's not getting up at 3 or 4 in the morning? What do you think we would care about when we're doing things in encryption? Is it safe? Is it secure? There's also another thing we care about in encryption. Easy to use. Speed. If it takes me 15 hours to transmit a message, is that bad? It depends. If I don't need an immediate answer, if it's something that can wait a while, I'm fine. How many people have seen Star Wars Rogue One? I finally saw it with my kids this weekend. That could be an interesting example of where you have a certain amount of time that you're willing to wait and not longer. So in a lot of times we need to know, can I do this under battlefield circumstances? Can I encrypt and decrypt messages in real time? And I might be willing to trade a little bit of security for efficiency, for speed. There are other things, such as maybe we're discussing long-term plans. Maybe we're talking about the liberation of Europe. Maybe we're talking about the D-Day invasion. We would be willing to say, you know what? I don't need a response immediately. A couple of hours is fine. Let's do the slower system that is a little bit faster. That's a little bit more secure. All right, so we're going to now move to elliptic curves. And so we've talked a lot about elliptic curves throughout the semester. We've mentioned a couple of things about them. This is going to be a good way to review a lot of ideas. This local to global idea of building up small bits of information at each prime, looking at these congruences, looking at this modular arithmetic, and getting this global object. So typically for us, an elliptic curve will be y squared is x cubed plus ax plus b. A and b for us will be integers. What you might actually do is you might replace a and b with functions. And then for every choice of the parameter for the function, you would get a different elliptic curve. You would then have a family of elliptic curves. These turn out to be extremely useful objects to study. And the first question you might ask is, does this have a solution? For general A and B, is there a pair of integers x and y that solve this? If not integers, are there a pair of rationals x and y that solve this? If not rationals, maybe some finite extension of the rationals, or maybe complex numbers. What do the solutions look like in different spaces? What do the solutions of x and y with complex coordinates look like? What about x and y with rational coordinates? What about x and y with integer coordinates? It turns out that there's a group law that you can associate to points on an elliptic curve. And we can build a more complicated group than RSA. So RSA encryption, what group did RSA use? So when we did RSA, what did that use?
P mod PZ star.
Yeah, RSA was Z mod PQ Z star, I think. We took like the product of two primes. And we had things related to this. There's going to be a group associated to an elliptic curve. Now the first question is, what do we get when we look at this over the rationals? What do we get when we look at it over the integers? Sorry, integers, rationals, reals, complex. Will this have complex solutions? If I give you an x, will there be a y that works? Yeah, it's easy to solve over the complex, right? Over C, it's easy. Y is just plus or minus the square root of x cubed plus ax plus b. Very simple to solve over the complex. You give me an x, and there will be two different y's that work as long as this is not 0. All right. Not a big deal. What about over the reals? What do you think about over the reals? What could go wrong?
X cubed plus ax plus b could be negative.
Yeah, the danger is, what if this is negative? So it's going to be y is plus or minus the square root of x cubed plus ax plus b if inside is greater than or equal to 0. So no matter what a and b I give you, will there always be an x where this is non-negative? So what do we know about the plot of x cubed plus ax plus b?
As limit as x goes to infinity is
So it's got to be going off to plus infinity as x gets very, very large, because the x cubed term will dominate. What about as x goes off to negative infinity? It's got to go down to negative infinity. Now things get interesting. It's possible to have different shapes. What's going to control the shape of where there are solutions?
the a and b.
The a and the b. And so through a and b, what are we going to get that's going to control what happens?
The zeros.
The zeros, the roots. So you've got to remember that there are some really annoying cubics. What's probably the most annoying cubic? It's got to be a simple one. This causes problems in calculus when you're trying to find maximum and minima.
X cubed plus x squared plus x plus 1.
Nope. But you start off right.
X cubed.
X cubed. X cubed is a bad cubic, right? Why is x cubed a bad cubic?
Because it has a point where the derivative is 0, but it's not a maximum.
Yeah. It has a place where the first derivative vanishes, but it's not a maximum or a minimum. The second derivative also vanishes here, so you have to go to the third derivative test. And it turns out that this is not a maximum or a minimum. You'd love to have the result that if the first derivative vanishes, you are at a maximum or minimum. No, you are at a candidate for a maximum or minimum. And this is why we have to be a little bit careful in calculus. What's going on here is we have a repeated root. How many real roots could x cubed plus ax plus b have?
3.
Could have 3.
Or 1.
3, what else?
2.
2.
Or 1.
Could it have 0 real roots? We know that this can't have 0 real roots, right? Why can't it have 0 real roots? It's got to cross the line somewhere. What theorem? I'm sorry? Not mean. Close. Intermediate. So by the intermediate value theorem, if it starts off negative here and ends up positive here, there must be a place where it crosses. You don't always have to go through certain values. The Celtics started off down, I think, 16-0 yesterday, and they came back and they won by 12. Must there have been a point in the game when the game was tied?
Well, besides the start.
Besides the start? No, why not? You can score in 1, 2, or 3 point increments. Right? I told one of my cousins I would work the Celtics game into the lecture. Right? What is the difference between the Celtics game, where the intermediate value theorem cannot assert that there was one point where the score differential was 0 other than the start, and in this case over here?
Cubics are continuous.
It's continuous. We have a continuous function. So you've got to be very careful when you use a theorem that you always remember what the conditions are. For the Celtics score, I don't know if there was some point in time when they were tied after the start of the game. You know, I can check and see if that happened, but it's not guaranteed because the score moves discontinuously. Here, because x cubed plus ax plus b is continuous, if I start off negative and I end positive, I have to cross. All right. So we can do a little bit more than just crossing once. We know from here, here's an example where we cross once. I can come up with examples where we cross 3 times. Is it possible to cross exactly twice?
Well, not crossing twice. Yeah, exactly.
I'm sorry?
You can't cross exactly twice. You have to, but you can. You have to like bounce off the.
So I could come in, have a double root, and come up like that.
Yes.
So I could have a double root. And in fact, if we wanted to, we could set it maybe as x squared x minus 1. And this will give me a double root at 0 and a root at 1. So I could have 3 real roots if one of them is a double root. So I'm hitting the x-axis twice. Is it possible to have just 2 real roots? So I want to count this root of 0 with multiplicity 2. And this is a big thing in number theory, is keeping track of how often a root occurs. Could I have just 2 zeros on the real line? Why not? I want a proof, not just a...
If you have 2, then you have to cross twice. The first time you cross, you're above the line. The second time you cross, you have to be back below the line.
Okay, so if I have just 2 like this, I start off negative, I cross again, and there's no way for me to become positive. The other possibility would be if I have a double root, I would not be able to end positive. So the only possibilities are we could have 3 real roots, with multiplicities, 1 real root. What if I gave you a quintic? What do you think?
1, 3, or 5.
1, 3, or 5. So it turns out there's a really nice theorem. So theorem. Let's let f be a polynomial of finite degree with real coefficients. Then the roots with imaginary parts occur in complex conjugate pairs. And so if I have some number z equals x plus iy, the complex conjugate of z is x minus iy. So if I have a polynomial with real coefficients, if 3 plus 4i is a root, then 3 minus 4i is a root. This only works if your polynomial has real coefficients. How many of you have seen this result? I've seen one person shaking their head positive. Raise your hand if you've seen this result. Okay, most people, okay. Given the number of people who haven't seen this, let's change the lecture today and let's quickly prove this. This is a good result to know. You should know a lot of these results about how to attack polynomials. Okay, so let's see. Okay, so let's see. Do I have a place here? So let's do proof. If you could all travel forward in time and take my complex analysis class, that would be really useful, or travel back in time and have taken it. I'm going to just state a couple of facts from complex analysis that I think are intuitively obvious and that you can prove by brute force. If you have a plus ib times c plus id and take the complex conjugate of the product, this is the same as a minus ib times c minus id. Does that seem reasonable?
Certainly seems that you can chat. That's good.
Right? How would you choose? You would just multiply everything out. Right? And so what it's basically saying is multiply everything out and then change all the i's to minus i's, or change all the i's to minus i's and then multiply everything out. So if this is the case, if I take z to the n and take the complex conjugate of that, what's that the same as? Right. Is I could take the complex conjugate first and then raise it to the nth power. And that's just basically using this again and again and again by induction. I can take two factors and then I would combine three factors as one factor times two factors and just keep propagating like that. Okay. The next thing is z plus w complex conjugate is z complex conjugate plus w complex conjugate. The complex conjugate of a sum is the sum of the complex conjugates. Okay. So now, let's say we have f of x is an x to the n plus a0. Okay? And let's say f of z equals 0. So that means, we have an z to the n plus a0 equals 0. What should we do?
So you have to take f of z conjugate.
So one thing is we could take f of z conjugate, or we could take the conjugate of the whole expression. Right? They're both going to be very similar. I think it's easier to take the conjugate of the whole expression. So if I now look at the complex conjugate of f of z, the whole thing, what's the complex conjugate of 0? 0. So what we would get is that we would now get an z to the n plus a0, complex conjugate of the whole thing equals 0. What's the complex conjugate of the sum? Sum of the complex conjugates. What's the complex conjugate of a product? The product of the complex conjugates. What's the complex conjugate of a power? The power of the complex conjugate. So we would get that this is now just an z bar to the n plus dot 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 plus a0 bar equals 0. At some point, it's nice to use the assumptions of the problem. Right? We've assumed that our polynomial is real. That should probably come into play somewhere. As an aside, if I give you the polynomial z minus I equals 0, I is a root, but I bar is not a root. But this is not a polynomial with real coefficients. Somehow the fact that I have real coefficients should come into play. Well, since I have real coefficients, the complex conjugates of these real numbers are just those real numbers. And so now I get an z bar to the n plus dot 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 plus a0 equals 0. So now I get f of z bar equals 0. And that finishes the proof. So if z is a root, z bar is a root. So the way they typically say this is complex roots occur in complex conjugate pairs. So since I start off with a polynomial of degree 3, I could have 3 real roots. Or if I have one complex root, if I have one root with an imaginary part, then its complex conjugate must also be there, and then I would only have one real root. So I have 3 real roots or 1 real root, and that's it. And I know I must have at least 1 real root because I start off at negative infinity and I end at positive infinity. So we know that there aren't that many possibilities. This is going to be extremely useful in trying to understand what's going on with an elliptic curve. Okay, so it's always interesting as to what do people still prove in high school and junior high when they do stuff like this. I will ask, we're not going to go into it. How many of you remember the rational root test? How many of you remember the alternating signs test? For that one, I actually have to put my hand like this. I vaguely remember what the alternating sign test is in terms of trying to determine when there are roots. If people are interested, email me, and I'm happy to just go over this stuff. It's not a bad thing to know as a math major, some of these old results. One of the things you might have noticed is that when I gave you the elliptic curve, is this the most general cubic? No, I don't have a coefficient in front of the x cubed, and I don't have an x squared term. Is it just the end of the semester and I'm getting tired? Well, that could be independent of whether or not I'm doing it like this. Why do you think I'm only writing x cubed plus ax plus b? And for those of you who've taken probability with me, this is actually similar to something we've done in probability. So the idea is, rather than setting a generic polynomial, is there a way to standardize things and bring it down to a certain class? And then I can just use something being in a certain form.
Well, you know, because the x squared term is 0, you know that the sum of the roots of x cubed should also be...
Well, the sum of the roots of the polynomial.
Polynomial of x cubed.
Right. What I can always do is, if I have an x squared term, let's say I gave you, x cubed plus alpha x squared plus beta x plus gamma. What I could do is I could look at a new polynomial, x minus c cubed plus alpha x minus c squared plus beta x minus c plus gamma. And now when I start to expand this, I'm going to get an x cubed plus alpha minus 3c x squared plus dot, dot, dot. And so I just choose c to be alpha over 3. So I can translate along the real line and eliminate the x squared term. And then the goal is to then try to rescale so that I can get rid of the term in front of the x cubed. So is everybody happy that I can just translate and rescale? So that I don't have to worry about an x squared term. I can always push my polynomial into this form, and as long as alpha was rational, I choose a rational c. Maybe not an integer, but a rational at least. So maybe I have to say, well, maybe a and b have to be integers. Well, it turns out there are tricks you can do to clear denominators. If I replace, if I send, let's see, x to d squared x, and I think y to d. Which way do I want to do this? D to the negative 2, and y to d to the negative 3y. So if I had y squared is x cubed plus ax plus b, I now replace x with x over d squared. So this would now become x over d squared cubed plus a x over d squared plus b. And this would become y over d cubed squared. I now multiply through by d to the 6th. And I get y squared is x cubed plus a d to the 4th x plus b d to the 6th. And so I can clear denominators. So I'm not going to go through all the steps as to why it suffices to study something like this. I want you to get a sense that there are these little transformations I can do, and I can assume my elliptic curve has a certain structure. And there's really not much of a loss in generality in doing that. And so in fact, if I had denominators, I can actually clear denominators by choosing d appropriately. So I can often still force things to be integers. The whole idea is I want to study the simplest possible representation. In the old days, when they were trying to solve things like the quadratic and the cubic, they did not like minus signs. And they would write the formulas different ways depending on whether or not they were minus signs. So they would have a bunch of sums over here equals a bunch of sums over here. And the reason was they thought of these as positive quantities, as physical quantities. You're not going to have a negative area. Now, of course, you could just look at it more economically. Well, this is positive assets, these are negative assets. And then the negative sign isn't so bad. So I have finally said something nice about economics. Only took 8 or 9 years at Williams. Well, I think once a decade is, I think, about reasonable. Okay? But this is a huge point. It may seem minor. It may seem, well, who cares why we're writing it like this rather than this? You spend a lot of time. And if you can reduce things to a certain form and start getting comfortable with that, everything looks the same. You can use the same techniques again and again. When we do things in probability, we often adjust our distributions to have mean 0, variance 1. If you remember Calc 3, and this is always dangerous, you like to parameterize moving along curves at unit speed. Then you don't have to remember, oh crap, does this formula have me dividing by the square root of the instantaneous speed? Well, if the instantaneous speed is 1, I don't care if I have to divide by it. I'm not going to make that mistake. It's really important to think about how you want to present stuff. So when we're looking at this, it is sufficient to study things of this form. So the big question, or the big questions. So question 1, are there 1 or 3 real roots? And question 2, is there a repeated root? So we know there's always at least one real root, right? If there is exactly one real root, is there a repeated root? Can you have 2 roots that are the same if you have one real root? No. The complex conjugate roots occur in complex conjugate pairs. I'm sorry, the complex roots, the roots with an imaginary part, occur in complex conjugate pairs. They're not going to be the same, and there's only one real number. If there are 3 real roots, could there be a repeated root? Yeah. How many ways could we have a repeated root if there were 3 real roots? There are 2 ways. What are the 2 ways?
All 3 are the same root.
All 3 are the same.
Or 2 of them are the same.
Or 2 of them are the same and 1 is different. So it turns out in those cases, the elliptic curve is called degenerate and has different properties. We want to figure out how things look. Imagine our elliptic curve has 3 real roots. Then it's going to look something like this. Right? This would be x cubed plus ax plus b. That would be my cubic. Now I want to take the square root of that. What would the square root of this look like? For which values? Let's call these roots R1, R2, and R3. Now, I'll draw it larger because this is really important. So I'm trying to understand the solutions. So here is R1, R2, R3. Here's x cubed plus ax plus b. Now we want to plot y squared is x cubed plus ax plus b. So which regions can there be a solution?
Between R1 and R2?
Yeah, between R1 and R2. And what else?
Greater than R3.
Greater than or equal to R3. So roughly, what is the shape going to look like between R1 and R2? So something like this. Anybody want to add anything to this? I mean, I could be just messing with you guys. Or there could be something you're missing. So you're trying to solve y squared equals this quantity. Let's give this quantity a specific number. Somebody give me a number for x cubed plus ax plus b. Give me a number. 5? Really? Fine.
Sure, 4.
4. Okay. Let's say that this equals 4. Okay. What number is squared to 4? 2 and negative 2. Right? So this is something I really want you to think about. There's a reason I'm spending so much time on this. Nobody was jumping out and saying, Professor Miller, you forgot the bottom. Why did we all forget the bottom? We are trained, when we see a square root sign, we are trained to think of the positive square root. You always want to be thinking about what assumptions are you making. I am sadly too honest at times to be allowed to be a professor. You know, I will freely admit that most of you are not going to use this stuff on elliptic curves. It's great stuff. It's wonderful mathematics. But this is not something most of you are going to use in the rest of your life. Being aware of assumptions that you are making, that is something that's very valuable. So in problem solving today, we were talking about assumptions we make without even realizing it, in just interpreting problems. And one of the big reasons for the crash in 2008 was because people assumed a math formula could be used in certain areas where they did not check to see if the conditions were met. Not surprisingly, the conditions were not met and things worked very badly. Over here, there's also going to be two solutions, and it's going to look, you know, maybe something like this going off to infinity. So this is what a typical elliptic curve is going to look like if it has 3 real roots. All right? So there's going to be a lot of stuff that we're going to be doing from this. And so it turns out if I take a point P here and another point, well, just because of how I've drawn things, I'll put the point Q here. I think we've mentioned this before, adding points on an elliptic curve. Did we do that earlier in the semester? And you know, we draw the straight line connecting them. We will hit the elliptic curve in one and only one other point. And it turns out that we call this point down here, the reflected point, P plus Q. So we will talk a lot about why this is the case. And this is going to give us a group law. This is going to give us a commutative group. So how many of you have, is there anybody here other than myself who has never taken abstract algebra? Am I the only one who has not taken abstract algebra? This is embarrassing. But I've at least taught it twice, so I think teaching it twice is enough.
You can count that as like sitting on it.
Yeah, I think so. What's interesting is I have a colleague who teaches at a school where they have programs to teach or train people to become certified as high school teachers. And she is one class short of being certified herself as a high school teacher. And it's a class that she herself teaches. And you can just imagine the ridiculousness of the situation, where the one class that, you know, if she could just take the class that she's teaching, she could become certified. So I will assume that people are familiar with the basics of group theory, what it means to be a group. We'll be getting into that on Wednesday's class. What I want to do right now a little bit is talk about when do we have a repeated root. So repeated roots. This is the difficulty. If we have a repeated root, things are bad. One of the things, you know, I love to emphasize is walk before you run. Instead of looking at cubics, what could we look at before cubics? Quadratics. What could we look at before quadratics? Linears. Okay, linears are kind of boring. If I want to study repeated roots, if I look at linears, it's not going to tell me anything.
There is one linear that has a repeated root.
There is one that has a repeated root. But so this now gets into your definition as to what is a linear. Do you have to have non-zero leading coefficient? And so if you say that I want to look at a linear equation and the leading term has to be non-zero, then there will be none. If you allow it to be 0, then there will be 1, and it will have a repeated root of degree infinity. But we don't really want to count the function y equals 0 as a linear function in this sense. Or better yet, it's not a degree 1 function. So let's study quadratics. So let's study y equals x squared. Well, I guess we could do the more general. I'll do x squared plus bx plus c. And we want to study this. Or maybe I'll call it maybe f of x. And I want to study, when does f have repeated roots? So do you know anything that will tell you when it has repeated roots? Yes? The discriminant. So the discriminant of f is what?
E squared minus 4ac.
Right, because in this case, a equals 1. So the question is, where did this come from? So typically we do things where the leading term is 1. And so the analysis is going to be a little bit easier. Let's write this as x minus r1, x minus r2. Right? We can factor the quadratic. So we actually can write r1 and r2 in terms of the coefficients of the quadratic. For those of you who've done group theory, did you hear the result that once your polynomial is degree 5 or higher, there's no longer a closed form solution for the roots in terms of the coefficients? Okay, beautiful, beautiful result. All right, so r1, it's going to be negative b, right? Plus or minus the square root of b squared minus 4c. R2 is going to be positive b plus or minus, all over 2a, right? Divided by 2. This is going to be b plus or minus the square root of b squared minus 4c over 2.
Shouldn't one of them be plus? It only has
Oh, sorry. Yes, sorry. Did it in the wrong spot. B squared plus b squared negative b squared minus. How can I get the discriminant from this? Do you see any connection between the discriminant and the roots? It's the part underneath the radical, but that's a tough thing to isolate. Is there a nice expression involving r1 and r2?
It's r1 minus r2 squared.
So it's r1 minus r2 squared. So if I look at the square of the difference of the roots, if that's 0, then I have a repeated root. So 0, repeated root. Not 0, distinct roots. Isn't this beautiful? If I want to know if there's repeated roots, I just calculate the discriminant. I mean, I'm a little disappointed that I don't see more smiles, high fives, people jumping up and down, smashing chairs, throwing kegs out. Why aren't people excited about this result? Isn't this wonderful? Why aren't you happy? So just because you've seen something nice before doesn't mean you can't be excited that it comes back? I mean, okay, I can understand that it's not as exciting because you've seen it before, but now we're seeing it at a higher level, we're seeing it. Why aren't you so excited about this formula? I have a nice way to tell.
You have to know the roots.
So one possibility is, if I know the roots, I look and see if this quantity is non-zero. Well, if I know the roots, why am I bothering to calculate this? Right? I already know whether or not I have a repeated root if I have the roots in front of me. Why would I do this? So this line here is true, but not that useful. Why is the discriminant useful? Because we can calculate the discriminant as b squared minus 4c. We can find the discriminant without finding the roots. That's what should cause the kegger to happen. That's what should cause people to be excited. Right? If the only reason that the discriminant is useful is because of this result, and the only way to compute it is by computing the roots, it's useless. And that's been one of the themes of this class. It's not enough to have something that's correct. We want something that's computationally useful. Because we can express the discriminant in terms of the coefficients of this polynomial, the discriminant is now extremely useful. And it's a very fast check. All I have to do is look at b squared minus 4c. If that's not 0, then I have distinct roots. And that completely solves the quadratic. What do you think the next thing we're going to have to do now is? Cubic. So we have a possibility for the cubic discriminant. And this is designed to finish right before 10:50 because it would be a shame to miss the punchline. The most general cubic is it's maybe alpha x cubed plus beta x squared plus gamma x plus delta. And you would then have a discriminant, maybe, if you had to, maybe I'll guess it's a product of 1 less than equal to I less than j less than equal to 3 of Ri minus Rj squared. This seems a really good definition of a discriminant. Look at all pairs of roots, take the differences and square. This should be some function of alpha, beta, gamma, and delta. Do you want to determine a function of alpha, beta, gamma, and delta? What would be so much nicer? Yes?
Well, first we like standardize it so we could just get rid of the alpha.
Yeah, make alpha be 1, so it's a real cubic. I feel like Pinocchio here.
Make call beta A or B.
0.
0,
Right? There was a reason we started, there was a reason we did all this crap in this, all this masterful analysis at the beginning of the lecture on why we want to look at x cubed plus ax plus b, right? Just make beta be 0, translate. Make gamma be a, and delta be b. How did we find beta equals 0? We just translated. Well, if we translate, are we going to change the difference in the roots? No. Because we're going to affect both of them the same. If we rescale, will we change the discriminant? Yes, but only by a multiplicative factor. If we rescale all the roots by a factor of 5, then each one of these factors is going to be changed by a factor of 5 squared, so we'd get 5 squared to the number of pairs. But it won't change whether or not it's 0 or non-zero. So the work we did to get to x cubed plus ax plus b, it's not going to change whether or not the discriminant is 0 or not 0. So the goal for Wednesday's class is we're going to talk more about the discriminant and use this to understand all these different elliptic curves we're going to study. We are going to be using the book, but I want to supplement and I want to add some stuff that's not in the book and really motivate why we're attacking problems this way. Okay, so I think this is a good place to stop.